This video briefly introduces a bandwidth enhancement and size reduction of a low-profile polarization reconfigurable antenna by utilizing multiple resonances. The proposed single-fed tripolarization reconfigurable antenna contains 4 square patches arranged in a chessboard pattern, an I-shaped top-loaded monopole fence and a microstrip line-fed cross-slot. The reconfigurability of the developed antenna is achieved by switching the state of pin diodes that are inserted on the cross slot and microstrip line. Taking the left-handed circular polarization state as an example, one can observe that the 3DD's axial ratio bandwidth of referenced microstrip antenna is only 1.9%. By using basic multiresonance antenna comprising 4 chessboard patches and cross-slotted ground, the 3DD's axial ratio bandwidth could be enhanced to 16.6%. Then, by loading an I-shaped monopole fence around the chessboard patches, forming a wider 3DD's axial ratio bandwidth of 30.1%. Thereby witnessing an improvement of 15 times compared with the conventional microstrip circularly polarization antenna. The understanding of the operating mechanisms of this antenna was developed using characteristic mode analysis. A basic multiresonance antenna comprising 4 chessboard patches and cross-slotted ground generates and excites 3 sequentially orthogonal resonant modes. An axial ratio bandwidth enhanced circularly polarization antenna with dual recances poles is developed. In order to make use of the slot line mode for further circularly polarization axial ratio bandwidth enhancement, an I-chip top-loaded monopole fence is loaded beside the chessboard patches to cooperatively regulate the slot line-based camp mode and the triple sequentially orthogonal modes to form a wider 3DD's axial ratio bandwidth. The optimized low-profile bandwidth enhanced polarization reconfigurable antenna were fabricated and measured. It is clear that the measured results are in good agreement with their simulate values. In summary, a polarization reconfigurable antenna with an overlapped bandwidth about 27.6% is achieved without sacrificing compact and low-profile characteristic, and in the future, we plan to design an electric small broadband polarization reconfigurable antenna.
Hi everyone, thanks for your interest in our work published in Actually Transactions. My name is Xumin Chen, and the other co-authors are Professor Yanhui Liu, Dr. He Zhu, Mr. Dingzhao Chen, and Professor Jie Guo, my current postdoc supervisor at UTS. This work focuses on developing a multilinear polarization reconfigurable antenna for 5G millimeter wave band applications. With this opportunity of ultra-hot in antennas and propagation, we will give a close look at this work. The basic configuration of the antenna is an L-field cavity excited by a waveguide feed. The desired operating frequency is at 29.25 GHz. As you can see, in the cavity, a resonant TM5100 mode is excited. On top of this cavity, we etch a circular array of the slots, and hence, this slotted cavity antenna is rotationally symmetrical with an angle of 36 degrees. To achieve the multiple LPs, we introduce a 2-layer copper clarity substrate above the slotted cavity. The substrate is hidden for clarity. The red patches are printed on the bottom layer of the substrate, and the blue patches are printed on the top layer. With this copper clarity substrate, the antenna achieves the high gain Fox beam with the copolarization along phi equals 36 degrees. Since this slotted cavity is rotationally symmetrical, we can achieve 5 reconfigurable LPs by mechanically rotating this substrate with the angle of 36. We can say from the pattern that this one, the saddle lobe level is a bit high, around minus 7.5 dB. To reduce this saddle lobe level, we add purple-colored patches on the bottom patch layer of the substrate. As we can see from the field distributions, this is equivalent to add in-phase radiating elements of the circular array. Thus, the saddle lobe level can be reduced to be around minus 13 dB. Based on this finalized model, a prototype was fabricated and measured. Here we show antenna prototype before and after assembly and the antenna measurement in anechoic chamber. You can refer to our papers for more details. If you have further questions or confusions, please feel free to contact us. Thank you.
Dear all, thank you for the chance to introduce our recent work about the low-cost reconfigurable 1-bit millimeter wave array. The idea of this work is to reduce the bit number of phase shifter. For a 1x4 linear array, the distance between each element is half a wavelength. We studied 3 cases. One is array with ideal phase, the black line. The other one is array with 1-bit phase, the blue line. The third one is the array with 1-bit phase and fixed phase, the red line. From the figures, we can find that for the array with 1-bit phase, the pattern of beam directions of 20 and 40 degrees has grating lobe, with gain reducing about 2 dB. As the fixed phase is applied, the grating lobe in the 20 and 40 degree beam directions are eliminated, and the gain is improved about 1 dB. To design a patch antenna with 1-bit phase shifter, a traditional slot-coupled patch antenna integrating 2 PN diodes is designed. The proposed patch has a slot on the ground, and a feeding line with 2 PN diodes. With selecting one of the 2 PN diodes in the on state, the feeding path can be changed between the left direction and the right directions. The left direction is state 1, and the right one is state 2. The simulated S11 at 2 states can cover the 25.5 to 27.5 GHz. For the 2 states, the E-plane and H-plane have the similar radiate patterns, and the radiated E field has 180 degrees phase differences, which is 1-bit phase shifter. With the antenna element, a 1x4 linear array is designed. To feed the array with the fixed phase, a 1-to-4 power divider with the fixed phase is designed. Also, the power divider without fixed phase is designed. For the power divider without fixed phase, the output port have same power and phase, while for the power divider with fixed phase, the output ports have same power with different phase. So, for the array with the fixed phase, the grating lobe in the 20 and 40 degree beam directions is eliminated with gain improvement of 1 dB. To validate the analysis, a prototype is fabricated. These are the patches, these are the PN diodes, and these are DC baseline. The state of 0, 20, minus 20, 40, and minus 40 degree beam directions are applied to test. Also, the frequency of 25.5, 26.5, and 27.5 GHz are measured. The measured result matched well with the simulated ones, so beam direction with 1-bit phase is achieved. Thank you.